All right, folks, so here we go. This is assignment 29, trapezoidal approximation. We'll get into what that language means. Suppose we had an integral from 2 to 5 of a function with respect to x. Now, I know this is going to seem a little backwards, but if you go to Roman numeral number 4, trapezoidal rule, all right, let's start out talking about the fact that an area under a curve, the exact area, as a matter of fact, would be to integrate that function over that interval. So if we were to integrate this function between 2 and 5, we'll get the exact area under that curve. Let's go ahead and take care of that first. So if you find the antiderivative of this, that would be x cubed over 3 plus 3x. And we would evaluate that from 2 to 5. All right, again, this is that fundamental theorem of calculus that we discussed. And then at this point, and again, I keep, all right, I'll do this. So, of course, then you put the 5 into your antiderivative. This is the evaluate part of the process. 5 cubed over 3 plus 3 times 5, and that would be the capital F of b, as you recall, minus, and then we put the lower limit of integration in there, the 2, and so that will give us 2 cubed over 3 plus 3 times 2, put 2 into there, f of b in our notes from before, and that's all just arithmetic. And if you perform all that arithmetic, which I did ahead of time, the exact area under that curve between 2 and 5 is 48 square units. All right, so you might be thinking, great, that's exact. Why do we need to do a different approach here? All you got to do is integrate the thing and evaluate and get your number. But here's the thing. Not every function is that easy to integrate, all right? We have lots of functions in the world that are just extremely difficult to integrate. I won't say impossible, but very difficult, all right? I gave you one that was very easy to integrate just so we could have a number to look at here. But I ask that you pretend with me that integrating that thing was not that simple. Suppose substitution didn't work. You will learn if you take Calc 2 that we're scratching the surface of integration. Substitution doesn't work on every one of these. There's all these techniques of integration that are out there, and not all of them work. So it's very possible that this step of finding your antiderivative is extremely difficult, all right? So just play along with me. But I'll keep this over here for cross-reference, that integral came out to be the number 48, and it was easy to integrate. Okay, so we'll keep that over here. That's exact. I need to make some room here. I will again appeal to you to pretend with me that you have a function that is not that simple to integrate. And therefore we want to do what's called a trapezoidal approximation, which is what we will build up to now. So, how would you use trapezoidal approximation to get an approximate value for the area under that curve between 2 and 5? That's the question here. Well, I guess the first thing I would suggest to you would be, and we'll need this for later on, and keep in mind that our function in this case would be that function over here, x squared plus 3, that we were integrating. I again ask you, pretend it's very difficult to integrate that function. Well, first of all, I guess I'd go ahead and plot the endpoints here. So mental arithmetic, if we were to put 2 in there, 2 squared is 4 plus 3. So that would plot over here at 7, right? Okay, 2 plots with 7. 5 squared is 25 plus 3 is 28. And again, the scale doesn't matter all that much. Just a rough picture of the question is all we're searching for here. So we have those endpoints there. And look, a generic function can do all kinds of undulations in between there and all that. So keep in mind, I'm giving you the specifics of a general discussion here. This one happens to be a parabola, and it opens up. So this would be the general appearance. This would be the somewhat specific appearance of that function over that interval. But keep in mind, a general function, one more complicated, could do all sorts of undulations in between. So here's the idea. We can take this interval from 2 to 5, and and we can split it up into subintervals and find the areas of trapezoids. So this is actually using a combination, in my opinion, of both algebra and geometry. So I guess the thing that I would just throw at you, and we're going to talk through a very brief discussion. I will just tell you that the major idea will appear on this screen. You already have it, as a matter of fact. So I'm trying to build this formula right here that's going to be on this screen as to how we do this. So the first idea would be that we would establish the general from geometry. What is the general formula for the area of a trapezoid? We're going to put some trapezoids on the picture here very soon. I'm going to make the left edge red, the right edge green, and the bottom edge orange, which I actually forgot to bring my orange marker, but we'll survive. Okay, so here's the deal. The formula for the area of a trapezoid, which we'll come back to, is 1/2 W times H1 plus H2 in parentheses, all right? So 1/2 the width times the sum of the heights for that type of trapezoid. This is a trapezoid that has right angles at the bottom. Not all trapezoids look like that, but they will on the picture we're about to draw. Okay, so that's the general thing to keep in mind. So here's the deal. If we're going to approximate this area here, we're going to divide that region into n subintervals, which is going to generate n trapezoids. And this is where, if you look back at the question, it said, split this up into 4 subintervals. It said n equals 4, as I recall. Let me take you back to the question just to make sure you understand what I'm saying. All right? When you do an approximation, you're going to subdivide this into n equal parts, n subintervals. And I will tell you how many to use, 4. All right? So if you think about that, the idea would be, if you want to find out how wide to make each one, if you're going to split this up into 4 equal parts, wouldn't you take the entire width of the interval and divide it by 4? So in general, the width of each one of these intervals for this question would be 5 minus 2, the width of the entire interval, divided by the desired number of subintervals. In general, it would be b minus a over n. Remember, we in general have called this a and b here, haven't we? I should have put that up earlier. But wouldn't you take the width of the interval, which is b minus a, and divide it by the desired number of subintervals? That's 3/4, otherwise known as 0.75. So each one of these subintervals is going to be a width of 0.75. So what I would tell you is, let's start with the 2 and just keep adding increments of 0.75 to it. So if you take 2 and add 0.75, your first subinterval is going to end there at 2.75. Okay, and we're starting to make some trapezoids out of this. Then you add another 0.75 to that, which gets you to 3.5. Another subinterval. Then you add another 0.75 to that. And these aren't scaled very well, but you get the idea. 4 1/4. Just keep adding 0.75. And then when you add another 0.75 to that, you get to 5. Okay, so that would be 4 subintervals there. And that's going to generate 4 trapezoids. Now, the reason we're going to apply that geometry formula we just talked about for the area of a trapezoid to this. But the thing you got to keep in mind is that these trapezoids have straight edges across the top. And so there's going to be a little bit of a variation between the actual trapezoid and the curve itself. So those blue edges that I made there are the trapezoids and, of course, the curve. This is why the area, if we add up the areas of those 4 trapezoids, it's going to be an approximation to the exact area that's under that curve. So that's the idea. So really all we do now is we apply that formula for the area of a trapezoid to each of these 4 trapezoids here. And if we add all those areas up, that should be pretty close, approximate, to the area under the curve. All right? So, a lot of hand waving here. Here's what I did in the notes. I put the left edge of the trapezoid in red and the right edge in green. So if you think about it, the first trapezoid, the left edge, would be found by putting 2 into the function, otherwise known as f of 2. And then the right edge of that first trapezoid would be found by putting 2.75 into the function. f of that number. That's how you get that edge. The second trapezoid, the left edge, would be to put 2.75 in to the function, f of 2.75, and the right edge would be found by putting 3.5 in there. So you see, again, what I'm trying to color code here is left edge red, right edge green. And so what I'm hopefully establishing for you as we transition across here is that each of these numbers in the middle are going to be involved in two trapezoids. 2.75 is going to be involved in, it's going to be the right edge of the first trapezoid, and later on, the left edge of the second trapezoid. And similarly for all these others, each one of these middle numbers is going to be involved in two different trapezoids. The right edge of this one, the left edge of the next one. And that's the thing to keep in mind as we develop this little formula for trapezoidal approximation. All those ones in the middle are involved in two trapezoids. However, the endpoints, the 2 and the 5, those are actually only involved in one trapezoid, aren't they? The 2 is involved in being the left edge of the first trapezoid, and that's it. And the 5 is the right edge of the last trapezoid. So keep that in mind. The endpoints are only involved in one trapezoid, whereas each one of them in the middle is involved in two trapezoids. And in general, we have our endpoints A and B, and we'll call these x1, x2, x3, and it just depends on how many trapezoids you're making. All right? So anyway, if you apply that formula for the area of a trapezoid to this situation, keep in mind the A and the B would be the endpoints of your interval, and the x1, x2, x3 would be those numbers in the middle. Given the fact that the endpoints are only involved in one trapezoid, whereas the ones in the middle are each involved in two trapezoids, and there's a lot of algebra involved in this, and this is all pulled together on the slide here where it says add up the areas of the first trapezoid, the second trapezoid, dot, 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 the last trapezoid. A little bit of algebra magic, because really it is just algebra going on there. It turns out that this ends up being the expression that will give us the approximate area for all those trapezoids. Well, this formula is the exact area of the trapezoids, which in turn would be an approximation for the area under the curve, as mentioned earlier. Notice that the f of A and the f of B are only in there once, because A and B, f of A, f of B, are only involved in one trapezoid, whereas all the ones in the middle are involved in two trapezoids. And that's why all the ones in the middle are multiplied by 2. But this is a combination of that general formula for the area of a trapezoid and the application of that area to each one of those 4 trapezoids. So, very cookbook now, the area of all those trapezoids using geometry, which is going to be an approximation for the area under the curve. Here we go. So B minus A over 2n. The 2 is there because I want to remind you that the formula here had a half in front of it. All right, so basically it's cookbook at this point in time. And so on this question, here we go, B minus A, 5 minus 2, B minus A, 2n, the fact that we had 4 subintervals. And then here we go, we've got f of 2, f of your left endpoint, plus, I'm going to run out of space here, it looks like. This might have some curvature to it in my setup. Sorry. 2 times f of 2.75. See, the x1 would be our first middle number, if you will. Notice all the middle ones get multiplied by 2. Plus 2 times f of 3.5. See, that's involved in 2 trapezoids. Plus 2 times f of 4.25. See, the reason we're putting it into the function is because we got to get the height of the trapezoid, and that's found by putting that number into the function. Notice all these ones in the middle are multiplied by 2. And then the 5, since it's only involved in one trapezoid, it'll just be f of 5 not being multiplied by 2. So again, the thing to keep in mind is that the left end point and the right end point of your interval are only in there once, and all the ones in the middle get doubled. All right, now, that's 3/8, blah, blah, blah. F of something is to put it in the function, 2 squared plus 3. We already talked about that this f of 2 would be 7. We already talked about the fact that this number would be 28, and then all the ones in the middle, you put them in the function. You square them and add 3, and then you multiply them by 2. So that's just arithmetic. I know that's snotty, but I think my job is to help you get the thing set up. And it turns out if you do all the arithmetic on that, and look, I've had multiple students in the past tell me I'm good from here. So, and I don't have a lot of space anyway, and it's just arithmetic anyway. But it turns out if you do all that arithmetic, these numbers, order of operations, put them in the function, take them times 2, add them up, all that, it turns out to be 48.28125. And you'll notice that's not the same as the exact, because again, integral gives you exact, whereas this is adding up these trapezoids. It's off a little bit, but it's remarkably close, isn't it? Not bad. So the question would become, how could you make that approximation even better? Well, I hope your intuition would tell you, if you made more trapezoids, it would be an even better approximation. So in theory, if you made 100 trapezoids over here, that'd be even better. I'm not going to make you do 100 of them. That's just brute force mechanical arithmetic there. But there's the idea. So the more trapezoids, the better. And so I guess we'll just come back and enjoy one more of these, and that ought to be it. All right.